Okay, welcome everyone to this video on the confusion between link aggregation and LACP. My name is Tony Bourke. I'm a networking instructor and I do videos and teach classes based on networking, network automation, primarily data center networking and some other data center related topics. You can find me on Twitter at tbourke, that's at TBOURKE, and I blog occasionally at datacenteroverlords.com. So let's start this video with an exam style question, like a certification exam style question. And the question is, what does LACP do? Does it A, combine multiple physical links to form a single logical layer 2 link? So multiple physical layer 2 links to form a single logical layer 2 link. Does it B, selects the hashing mechanism to use to divide traffic between physical links in a logical link? C, both A and B, or D, none of the above. Now, given what I've seen in terms of how people have described this technology, I think most people, including myself at one point, would have selected C, both A and B. It sounds logical, but it's actually not correct. The answer is D, none of the above. LACP doesn't do either of those two things. So what the issue is there's a confusion between the term LACP and link aggregation. So when people say LACP, they're often really describing link aggregation. So, and I think that this video is meant to clear up the confusion between the two, because when you use the term LACP to describe link aggregation, I know what you mean, and I think most people know what you mean, but I think it does help to go over why there's confusion and just understand things a little bit better. So that's what this video is meant to do. So, like I said, when people say things like LACP load balances packets, LACP is configured for a layer 2, layer 3 hash, LACP can increase total aggregate bandwidth, LACP doesn't load balance per packet, it does it per flow. That's all incorrect. None of those statements are correct, and those are stuff I see online all the time. Now, if you replaced LACP with link aggregation, they would be correct, because that's actually what link aggregation does. So what LACP doesn't do is it doesn't divide traffic between links. It doesn't select or even influence the selection of a hashing mechanism. Now, there is an update to the link aggregation standard that includes LACP, that has a new TLV that includes the ability to suggest or report which hashing mechanism is used. But as far as I know, no vendor uses it or has implemented it. And you can have lag without LACP, and they're not the same technology. So what is link aggregation? It's an IEEE standard, 802.3AD, and that was set in the year 2000. It has since been moved to 802.1ax, and it's been updated a few times. There's a version from 2008, from 2014, and 2022, so that's actually fairly recent, just last year. But most of what we're talking about is going to be what's based off of 802.3AD, so most implementations pretty much use whatever those. There's a couple new things in these various updates, but everything that we do from day to day is pretty much was what was in 802.3AD and has been carried forward. Link aggregation is a standard. It is used to connect routers, switches, hosts, hypervisors, firewalls, load balancers, etc. So it's used for multiple vendors, for multiple different types of technologies, and we can use it to connect any kind of device to any kind of device. It's going to aggregate multiple physical links into a single logical link, and that is called a LAG, link aggregation group. And typically at least 8 links are supported in a LAG, but some platforms may support more. So a link aggregation group is the name for an individual instance of LAG. Cisco and Arista would call this a port channel. There are some other vendors that call it a trunk. Although most vendors, when they use the term trunk, they actually mean multiple VLANs over a link, 802.1q. But in this case, we have 2 devices, and they're connected via 2 different lags. So a lag is usually denoted by that circle there. A couple of features of link aggregation: it divides traffic deterministically between the links via various hashing mechanisms. That's done to make sure that things are delivered in order. It works with multiple vendors. Like I said, delivers frames and orders. And a single logical link will appear to be a single path from a spanning tree protocol perspective. So one of the rules that we have in layer 2 networking is never let there be more than one path. And this gets around it by providing a single logical path from a spanning tree perspective. So spanning tree is used in conjunction with link aggregation, and it's just making sure that we don't have loops elsewhere. But link aggregation will allow all 4 of these links in this case to pass traffic without blocking any. So what about LACP? It's a part of link aggregation. It's an optional part. It was defined as part of the original 802.3 AD specification and is still part of the updates 802.1ax. If you do LACP, they're considered dynamic lags. If you don't do LACP, they're considered static lags. So you can still do the same link aggregation with or without LACP. So how does link aggregation actually work? So it works by making adjustments to some of the standard layer 2 forwarding rules. And by adjusting these rules, we can make multiple links appear to be a single logical link, and then spanning tree sees a single path. Multiple links forward without causing the typical issues that you get when you have multiple paths active. So there's no MAC flapping issues, no broadcast storms, etc. So before we talk about how we adjust the rules, let's talk about the rules and why we have the rules. If there's more than one path in layer 2, typically we have what's called a bridging loop. Now, sometimes people will erroneously refer to this as a spanning tree loop. Spanning tree is actually what prevents the loop. So technically it's a bridging loop, and they cause 2 general network breaking problems: broadcast and flood storms, or broadcast/flood storms, and MAC flapping. Now, the broadcast storms also will affect the hosts on a given layer 2 network because they have to deal with all of these. They have to look at all these broadcast packets, evaluate them, then throw them away because they're not relevant to them, or they have to do something with them, like maybe it's an ARP flood that gets replicated, etc. So it causes all sorts of bad things, and bridging loops are bad. They generally will take down a network. So why do they happen? Well, when a frame enters with an entry in the forwarding table, so a frame enters a switch, if there's an entry in the forwarding table, we're going to forward that frame to the interface listed in that forwarding table. Pretty simple. When an unknown unicast frame enters a switch, we are going to flood it out all the interfaces except for the one it arrived on and write the source MAC address into the forwarding table. When other types of flood frames, so an unknown unicast is considered a flood frame. A flood frame means we're going to make copies of that frame and send it out all the other interfaces. There's other types of flood frames, broadcast and multicast. When it gets entered into a switch, again, we're going to flood that out all the interfaces. There are some mechanisms like IGP snooping that will adjust this behavior, but that's the default basic behavior. And this can all be done on a VLAN aware basis. So it's all done, all this flooding is only done in a particular VLAN. So let's take a look at what causes the MAC flapping. So here we've got a host. It's going to send a flood frame. Maybe it's a ARP, some sort of broadcast. Doesn't really matter what it is. But the rules are when we get any kind of frame that we're going to flood, it comes into the switch. We're going to make 1 copy per these interfaces. So we've got 4 copies. It's going to go over to switch 2. Now, they all came from the same source MAC address. So what is switch 2 going to do? Well, it's going to write down the MAC address. Came on Ethernet 1. No, it came on Ethernet 2. No, it came on Ethernet 3. Nope, came on Ethernet 4. So it's going to bounce back and forth depending on if one frame was received slightly quicker than the other frame. This is going to cause a lot of flapping. If I'm sending frames to that MAC address, I can't tell which interface it's going to go over. Just whatever the forwarding table says at that exact moment. It's going to cause a lot of CPU writing to that forwarding table, a lot of instability. It's a bad thing to happen. So let's talk about the broadcast storm. Broadcast storms are even worse, I think. So again, we get a frame that comes in. We're going to replicate the frame 4 times. So these 4 frames go down to switch 2. Now they're going to get replicated as well, and they're going to get replicated 3 times because it comes in on one and then out the other. So now I've got 3 copies of the frame that are going to switch 1. And then all 3 of those are going to get replicated 3 times. And I've got 9 copies. And then I've got 27 copies, 81 copies, 243 copies. Now we've got this broadcast storm. We're filling up the network. We're overwhelming the interfaces. We're probably dropping frames by this point because all this is happening at pretty close to line rate. And it's going to overwhelm the hosts on that network because they're getting line rate of flood frames that they have to evaluate and decide that they don't need to do anything with, or doesn't have any information that they can use. So it's a bad scene all around. So we want to avoid these 2 things. And that's what Spanning Tree was built to do, is to prevent these multiple paths from happening. Spanning Tree would go in and disable, first it would disable all the interfaces, and then it would only allow one of them to forward. So how can we tweak the rules of Ethernet, of layer 2, in order to prevent these 2 bad things from happening, but still allow the traffic to pass? So here's what we're going to do. So when we receive a frame on a lag interface, when an address is learned, the source port is recorded. So it comes in as an unknown unicast. We're going to write it to the forwarding table. But instead of writing it as the interface it came in on, if it's part of the lag, we're going to write down the lag interface, not the individual interface. And then when we get a flood frame, so broadcast, unknown unicast, multicast, a bump frame, when it's received on a lag interface, we're going to flood it, but not out of any of the other interfaces that are part of that same lag. So we're not going to send it out the same lag that it came in on. When we're going to send frames on a lag, we're going to use a deterministic method to pick the link so that the frames, so that all related frames go over the same link. This is to make sure that we do in-order delivery. And then if we have any flood frames, we're only going to send them over a single link. We're not going to send it across multiple links. And also, here's an interesting thing. This is going to come up a couple of times. The sending side of this link aggregation is the only side that has any say on which link that any traffic goes over. So the sender is what chooses. It's going to come up in a little bit. So let's look at receiving frames, how we're going to do learning on a lag. So when an address is learned, they're learned as the lag interface instead of the individual interface. So I've got 4 interfaces here. They're part of the same lag. So when a frame comes in on a different individual interface, but of the same lag, the forwarding table is not changed. We're going to update the timer, but we're not going to update the interface it came in on. So for example, we get a frame that comes in on Ethernet 1. It's a new address. We don't have it in the forwarding table. The source MAC address is 00 and then all A's. So we're going to write that into our forwarding table, and the interface is going to be lag 1, not Ethernet 1. A subsequent frame comes in, same address, just got hashed to that link. We're not going to update the forwarding table. We're going to update the timer because eventually we're going to time things out if we haven't heard from this MAC address in a while, but we're not going to update the entry. And then if we get a new frame that comes in on Ethernet 3, then we're going to write that down as well on, and it comes from a different source MAC address, and we're going to write that down as an entry, and it's going to come from lag 1. So that way, if I want to send a frame to one of these MAC addresses, I'm going to hash it out one of these 4 interfaces off of lag 1 rather than the individual interface. So that's going to prevent the MAC flapping. How about the flood? So when we get a flood frame that comes in off of that lag, we're going to flood it out all the other interfaces, but it's not going to go back into the lag. So this will prevent those broadcast storms that we're talking about. And then when we are sending so this is receiving a flood. When we're sending a flood, we're going to do a deterministic hash to figure out which one of these interfaces we're going to send that, or some method to pick where we're going to send that flood. We don't send it out all 4 at the same time. We just send it out 1. So here we got 2 different flood frames. One goes up Ethernet 1, one goes down Ethernet 3. No problem. And then for unicast, the sending switch picks a single path for a known unicast frame using a some sort of deterministic hash. And that's again done to ensure in-order delivery. So any related frame, so if it's part of the same TCP connection or UDP flow, we needed to go through a single interface. And the reason is we're going to go through a single queue and a single buffer It's kind of like if you're in line at the grocery store or the security line at the airport. Different lines have different lengths, and it will take a different amount of time to go through each line. So if you are part of a group and you split up across the lines, the order that you enter the lines may not be the order that you get through the lines. So in order to ensure in-order delivery that everyone stays in the same order, we're single file. So let's take a look at this in action. So here we've got MAC addresses that have been learned. We've got two hosts. Host 1 is connected to switch 1. Host 2 is connected to switch 2. And all the MAC addresses are learned in the forwarding tables. In order to get to host 2, which is B's, we know that we go across lag 1. That's what this is right here. So a frame is received by switch 1. The forwarding table says the destination port is lag 1. We make a deterministic determination on which of these interfaces to send that frame over. It gets into switch 2. The destination MAC address is all B's, and it gets delivered to Ethernet 5 because that's what the forwarding table says. The response goes pretty much the same way. Host 2 is going to send a frame to host 1. The destination MAC is 00 all A's. So 00 all A's means lag 1. We're going to send it across that link. Now, it went across a different path than it came in on, and that's perfectly okay. We will often have asymmetry. In fact, most of the time, flows will be asymmetric. There may be cases where they're symmetric because we have matching equipment on both sides and configured the identical ways. But generally speaking, it doesn't matter if we have that asymmetry. So about this hashing mechanism, it's a bit of a mystery. There are many ways to choose a path for a frame. The main requirement is that related frames travel the same physical path, and that's to facilitate in-order delivery. That's really the only requirement. Most devices offer a variety of header fields to feed that hash, and they're configurable. So things like source and destination MAC address, source and destination IP address, source and destination TCP and UDP port, where typically most switches default to hashing all these together. We can add some other headers in there too, like VLAN tags. As long as we deliver stuff in order, it kind of doesn't matter. There are some hashing mechanisms that are better than others, depending on what kind of traffic flows, etc. But we want traffic divided roughly evenly, and we want in-order delivery. So as long as our mesh mechanism supports that, then it's fair game. Also, each hardware platform may do this mechanism slightly differently. So the math that they do, the hashing mechanism, the modulus, etc., XORs, they may be different and often will be. And even different models of switches by the same vendor will have different options. If you've ever dug into some of the commands to specify these hashing mechanisms, most of the switches, most of the vendors will have very platform specific based on whatever forwarding engine is in that particular switch. And the sending side is the only device in the connection that has any say in that hashing mechanism. The other side cannot influence it. It only just receives those frames and then delivers them where they need to go. And the hashing mechanism is not communicated in any protocol, not even in LACP. Now there is, if I remember correctly, 802.1ax 2014 does have a TLV that includes the hashing mechanism. But as far as I know, no vendors implemented that, so it doesn't matter. And that's okay. Even common for there to be asymmetry in these hashing mechanisms. I'll give you probably the best example I can think of from VMware. So if we're going to do a lag with an ESXi or a VMware hypervisor, so their vSwitch, we can do a lag. The way that it calculates which path a packet will take on which uplink, the virtual switch will take the last octet of the source and destination IP address. Now, I don't know of any physical switch from any vendor that just uses the last octet. As far as I know, every one of them uses the entire IP address, but VMware only uses the last octet. It puts them through some sort of XOR operation, and then runs the result through another calculation based on the number of uplinks on the NIC team and modulus. And this is from the VMware documentation. So this is a very different method. So I've got a switch here on one end of the lag, and traffic going to the host to the hypervisor is going to be load balance. It's going to be hashed across the source and destination layer 2, layer 3, layer 4 header. Whereas from the host, we're just doing layer 3, we're just doing the last octet, and we're doing an XOR and then probably a modulus. And so we have that asymmetry, again, very, very common. And it's okay. It doesn't matter if one side's configured one way and one side's configured the other way, because the receiving side, it's all its responsibility is just to deliver the frames that it received to the proper place. Again, we're just tweaking the rules a little bit on what we do with that information, what we do with the broadcast frames, etc. Another thing that I run into is what I call a technology anachronism. So these are things that were once true but aren't true anymore, at least mostly not. And one of those that I've heard, not heard, but this is a rule like 20 years ago, but is no longer a rule today for most equipment, is the power of 2. Now, this was a power of 2 because when a switch would hash on a link aggregation group, on a lag, on a port channel, Cisco or Arista, you only had 8 outcomes, 8 buckets in order to put the traffic into, and you had to divide those 8 buckets across how many links you had. And it only worked out evenly if you had a power of 2. So if you had 2, you would have 4 on each one. If you had 4, you had 2, and if you had 8, it would be 1. So that would be the power of 2. If you had, for example, 3 links, 3 outcomes of the hash would go to this link, 3 of them would go to this link, and only 2 would go to this link. So link 3 would get less the traffic than 1 and 2, at least from an algorithmic basis. So, I mean, you could do it, and if you had a link failure, for example, if that link went down, then they would just migrate to that, and it's fine, but we generally don't like this much asymmetry in our traffic patterns. That's not really the case anymore, because most hardware today does not require lags to be a power of 2. Older hardware had that XOR hash, like I said, that gave you a 3-bit value. That's 8 buckets. 3-bit, 2 to the third power is 8. With only 8 buckets, traffic only had the option of 1 of 8 outcomes. So that's the how we can separate those buckets across the multiple links. Most modern hardware uses more robust hashing mechanisms, including a deeper hash. Most of the equipment that I've searched for from the various vendors, Cisco, Juniper, Arista, it's not documented how many buckets you get with the bit with the hash bit depth is, or how many outcomes, or how it does the math. But if it does do math, it does come out to a hash. I did find one vendor that it was a line card for a Nexus 7000 from Cisco, and they had a line card that did an 8-bit hash. If you have an 8-bit hash, you can divide traffic more evenly, even across non-powers of 2. So, for example, if we have a 3-bit hash and only 3 links, that's 332. So that's a pretty big imbalance. With an 8-bit hash, we have 86, 85, 85. So 86 of the outcomes here, 85 of the outcomes here, 85 of the outcomes here. It's like a 1% difference. So it's not really a big deal, where this is a much larger percentage of the difference. So basically the story here is that modern equipment does the hashing in a more robust way, so we don't have to worry about powers of 2. So you can have a 3-link port channel, you can have a 5-link, 6-link. It's fine. Don't worry about it. Another takeaway from link aggregation is that all we were doing is we were adjusting the rules of layer 2 forwarding. There was no communication necessary for this to happen. Link aggregation is a standard and not a protocol. Now, there's an optional protocol that's LACP, but the actual dividing traffic, sending traffic, etc., that's a standard. It's an agreed upon set of behaviors. So an analogy for this that you might be familiar with is just driving down the road in a car. In North America, in lots of Europe, and other parts of the world, when we drive down the road, we drive on the right side of the road. The oncoming traffic also drives on the right side, so it's the other side from my perspective. And that's an agreed upon set of behavior. There's no protocol necessary for me to communicate with the oncoming traffic to be like, you should go over here or over here. It's an agreed upon set of behaviors. And then, of course, in other parts of the world, like the United Kingdom, Ireland, other countries, they do the opposite. But what's important is that everyone agrees upon which side of the road we're going to drive on, at least for that particular region. So there's no protocol that's happening to make any of this work. So everything we've just talked about so far, then the hashing mechanisms, how we do flooding, etc., that's all configured on the device, and there's no protocol for this. Think about how we populate MAC tables and forwarding tables and switches. There's no protocol for that. It's all done just by our agreed upon set of behaviors. All right, so where does LACP fit into all of this? Think of LACP as kind of a miscabling protocol. It doesn't do what most people kind of think it does, but it's actually pretty important, and it can save you from a couple of mistakes. So it is optional. You don't have to run LACP, but I always do. There's a couple of exceptions where I don't, but if it's an option on the equipment, if both sides support LACP, then I'm going to run LACP. LACP sim will send LACP PDUs across all the LACP-enabled links. That information is critical for making sure that we're plugged into the right thing, because it would include something like a system ID, so identify the system that we're connected to, and an interface lag ID, so the bundle ID. LACP is generally just used to ensure that the devices are connected to the correct devices. There's a couple of other edge cases, but we're not really going to get into that there. Most of what we use it for is basically to prevent miscabling. So here's LACP in action. Each side is sending their PDUs to the other side. And like I said, part of that information, there's a bunch of information in those PDUs. There's a unique system identifier. There's a system priority. There's a unique link identifier, link priority, interface priority, or maybe not link priority, but interface priority and some other stuff. We mostly concerned about the system identifier. That's what's really important to what we do. So for example, I've got these two switches, switch 1 and switch 2. Both of them have a system identifier. So some way to identify the system. Most of the vendors use the same MAC address that they use for the bridge ID. So most vendors, their switches will have some sort of system MAC address, system ID, and that's what we use here. The system ID is actually, technically, it's a combination of the system MAC address as well as a priority, but we don't really care about the priority. Priority is used for when not all the links are active in a lag. Some links are standby, but in the data center, the campus, it's not something, I don't think I've ever seen anyone do standby links. Might as well, why would you want standby links? Just light everything up. So in this case, there might be some edge cases to do that, but I've never seen it used in production. So switch 2 is sending PDUs over to switch 1, and then here we do a show command on switch 1. This is actually the output from an Arista EOS device, but this output, there's some variation of this output for every vendor that does LACP. And this command was show LACP peer, and that we can see that Ethernet 1, 2, 3, and 4, these 4 links here, we are receiving the same system ID. This is the important part right here. If they were different system IDs, this would means we're not plugged into the same device and something has gone wrong. There's also the port ID on the other side, and the opper key. This is which lag we're doing. This is just lag 1. There's also port priority, but again, we don't really use that kind of stuff. In this case, we've connected the 2 devices to 2 different lags. So you can do this. There might be some cases where you want to separate out your 4 links into 2 individual bundles. So we just have 2 port channels, or 2 lags rather, and we're getting the same system ID across both, but to differentiate them, we have that different lag ID here, this opper key. So how is this going to help us out? So let's say, for example, I've got 2 switches and somebody made a mistake. Maybe I made a mistake. I plugged switch 1's link 4 into a coffee maker. Now, without LACP, if I do just a static lag, if the link light is up, then we're sending traffic down the lag. So I've got all 4 links link lights up. I've got the link light because I've plugged into a coffee maker. I don't know why this coffee maker had like a 100 gig interface, but it did. And I'm going to send some traffic. So I've basically black holed 1/4 of my traffic. So 1/4 of the traffic is going to end up at, not exactly 1/4. It'd be algorithmically whatever the buckets were. They're going to go to the coffee maker. The coffee maker is not going to know what to do with it. It's going to drop the frames. So we've ended up black holing 1/4 of our traffic. So that's without LACP. Without LACP, this is a static lag. And then with the static lag, if there's a link light, we're sending traffic down that link. So what about with LACP? With LACP, we're getting the system ID from the 3 links, but we're not getting a system ID. We're not getting LACP PDUs from that 4th link because the coffee maker probably is not running LACP. And even if it was, it would have a different system ID. And LACP is checking to make sure that the system IDs match, and it would block the interface. It would basically turn it off, and it wouldn't send any traffic down. So I'm only using 3 links on both sides, and this link is disabled. And I can see that in a show command. And if I'm wondering why traffic is doing what it's doing, I can take a look there. But I'm not going to black hole any of my traffic. So if I look at the show command, show LACP peer, I think the all interfaces switch. We can see that 3 interfaces are bundled. We have the same system ID, but we're not getting any LACP PDUs from Ethernet 4, so it's unselected. We've dynamically removed it from the lag. So we're not sending it any traffic, and that's basically what we use LACP for. There's a couple other edge cases for what it can be used for, but this is primarily what we use it for. So in the data center and the wired campus, there's very few reasons not to use LACP when configuring lag. This video has probably really downplayed the importance of LACP in your mind because all the magic happens in link aggregation, but it's still a good thing to turn on. I turn it on anytime I'm using link aggregation. It doesn't affect the performance of the links, not making the packets happen quicker, or move faster, or anything like that. It's just there to kind of keep an eye on things in case you make a mistake. So, and there's a couple other things that LACP can do. There's interface priorities and system priorities, and we just don't really care about that for the most part because all the links are going to be active. We're not trying to figure out which links are going to be standby and which are going to be active. Part of what I think is the issue here is the confusing terminology. There's a lot of confusing terminology around LACP and link aggregation. And it doesn't help that the other vendors might use their own terms. So, for example, link aggregation itself is known by a lot of other terms. It was called Ether Channel by Cisco for a long time. And Ether Channel actually predates link aggregation. They came up with, Cisco was doing this before there was 802.1 3AD. And they called it Ether Channel. And when they created, when the IEEE created the standard, Ether Channel was compatible with it because, again, all Ether Channel was doing was just tweaking those forwarding rules. So Ether Channel worked immediately with link aggregation, except for the LACP part, because Cisco had their own, they called it PAGP, but they adopted LACP, and some of their equipment doesn't even do the PAGP, like the Nexus switches, they only do LACP. So Ether Channel was a name for it. Cisco doesn't really use that term as much anymore. Port channel, this is usually referring to an instance of link aggregation, like a lag. That's what Cisco and also Arista call a lag, is a port channel. But it can also be used by Cisco to refer to the technology itself. I think I mentioned earlier, some vendors use the term trunking instead of link aggregation, which is super confusing because most of the other vendors, when they talk about trunking, they're referring to multiple VLANs on a single link or a single logical link. Whereas some vendors consider trunking, taking those physical links and turning them into one logical link. So a little bit confusing there. The server vendors and the hypervisor vendors also have their own terms. Microsoft calls link aggregation, they call it switch dependent NIC teaming. Static mode uses no LACP, and then they have LACP mode, which does use LACP. They have switch independent mode, which is not link aggregation. It's another type of dividing up traffic. It's not as good for the most part. But the advantage there is you just configure regular switch ports. In Linux, we have that's called NIC bonding. Bonding modes 0, 2, and 3 are static lags. Bonding mode 4 is LACP. So they have multiple modes. Some of them are link aggregation. Some of them are not. Some of them are just other ways to divide up traffic. And the switch ports would be configured as just regular switch ports. And then VMware, they call link aggregation route based on IP hash. So I think they win for the weirdest, the name that doesn't resemble what the networking world calls it, what the IEEE calls it. So route based on IP hash. It's a static lag, and you can optionally turn on LACP, but it has to be on a distributed virtual switch. Generally speaking, in VMware, there's two types of layer 2 switches, the standard virtual switch and the distributed virtual switch. LACP is only supported in the distributed virtual switch, which means you have to pay VMware extra money to use that kind of switch. They also have route based on virtual port ID, which is the default, or route based on MAC hash, which is very similar to route based on virtual port ID. And we're pinning virtual machines to a particular uplink. And they would be configured as regular switch ports. A lot of VMware shops do this. They don't actually do a lag to the host. But the effect is the same. We're using multiple links, they're active, etc. So I hope. Thank you for watching this video. It's a pretty long video. It's 36 minutes. I hope you learned something. I hope this was beneficial to you in some way. My name is Tony Bourke. You can find me at datacenteroverlords.com. You can also find me on Twitter at tbourke. And thank you for watching. Thank you for sitting through this. Hopefully this helped you out.